Okay, now let's continue with the discussion about lenses. There is a second type of spherical lens that's called a concave lens, and here is a cross-sectional view of the concave lens. So the lens, the glass part, is between these two surfaces. So you see the surface caves in instead of bulging out. Let's see what happens to this type of lens. Okay, again, there is an optical center such that any beam that's aimed at the optical center goes right through, and I can draw an axis parallel, perpendicular to the surface of the lens, and pass it through the optical center. That's called the optical axis, as usual. Now, let's think about a beam that is parallel to the optical axis. Again, assuming it's near axis. Let's see what happens. It's going to be refracted twice by this surface and then by that surface. Okay. For the first surface, let me draw a normal here. So that's the normal. The incident angle is this much. Okay, because it's getting into the lens. The refracted angle is somewhat smaller than this, right? It's going to be somewhat smaller than this, so it's going to go like this, okay? Because this angle has to be smaller than that angle. Okay, so it's going to land at that point where it's going to get refracted again. So here is the new tangent, and here is the new normal. This is the incident angle, right? The outgoing angle this time will be bigger because it goes from lens back to air, so it's going to be going that way. So you see, with each refraction, the beam gets bent further away from the optical axis, upward, and another beam will go downwards. So you see, this is different from a case of a convex lens. In this case, the light rays parallel to the optical axis will get reflected away from the optical axis. They're not going to focus anywhere on the optical axis on the other side of the lens. Rather, they're going to diverge. Okay. For this reason, a concave lens is also called a divergent lens. Just like the convex lens is oftentimes called a convergent lens, okay, or focusing lens. Now, what if you put your eye here? What are you going to see? Well, you see a beam coming this way. In fact, I can draw another beam coming in like that. Okay, these beams will never converge on the opposite side of the lens. Rather, they will just diverge. But to the eye here, it appears that these beams somehow started from a certain point here. Right? Now, is there really any light rays coming from that point? Of course not. Light rays are actually parallel to the optical axis. So this is a virtual focal point. Okay, a virtual focal point. Imagine you have a distant object casting parallel light rays aimed at this concave lens. You look through the lens, you will see an image of that object, such as a distant tree or the sun. This is a virtual image somewhere here. Okay, so it appears there is a miniature tree or miniature sun at this location, even though nothing is really there. That is a virtual focal point. Alright, given this idea, we can now draw ray diagrams to form an image of any object by a concave lens. I have here a virtual focal point. Right? Now suppose I have an object here. I want to know where the image of this object is. Okay, again, two rules. Rule number one, a beam that is parallel to the optical axis. What's going to happen? Well, if it's a convergent lens, you know what's going to happen, right? It's going to converge at the real focal point. But here, it's the other way around. It's going to diverge like this. But if you extend this line backwards, it's going to go through the so-called virtual focal point. So it's like this. Okay, that's light ray number one. What about light ray number two? Well, if you aim at the optical center, still same thing happens. It goes right through. It simply goes right through. Okay, so these are the two representative light rays coming from the tip of the object. You put your eye here, what do you see? You see one light ray going this way, one light ray going that way. They appear to be from where? They appear to originate from this point. Right? This point. So this is the location of a virtual image. Make sense? Okay, it is a virtual image. Not only is it virtual, it is the right side up. Okay, so it's virtual upright. Is it bigger or smaller? It's obviously smaller. Minify. can test the ray diagram by drawing an object anywhere on this side, with p greater than 2f, within 1f and 2f, or even less than 1f, whatever you do. No matter what you do, you find there is only one type of image you can possibly form out of a concave lens, and that is always virtual, upright, and minified. You know what? This reminds us of a certain type of mirror, right? Is it convex or concave? Concave mirrors behave very much like convex lens, right? But a convex mirror, just like a concave lens, can produce only one type of image: virtual, upright, and minified. Okay? So, again, concave lens behaves like a convex mirror, and a convex mirror, and a convex lens behaves like a concave mirror. Okay, as far as the lens equation is concerned, just like the case of mirror equation, I can still write 1 over f equals 1 over p plus 1 over q, even for the concave lens. Now, we didn't derive it, but if you were to do so, you'll find the same exact formula holds true for both concave and convex lens, except what? The value of f. F has to be negative to make it work for this type of geometry. Okay, for this type of geometry. So if I give you a lens which is marked negative 5.0 centimeters, you know what that means? Okay, it is a lens, a focal length negative 5.0 centimeters, which means it's a concave lens. Okay, so a concave lens is called a divergent lens. It is also called a negative lens because f is negative. And a convex lens is often called a positive lens because the focal length is positive. It is often also called a convergent lens because it can focus light beams instead of diverging it. Okay, so these are discussions of spherical lenses. Okay, I have a couple of cases that I want you to pay attention to as well. One is the idea of the so-called virtual focal plane. With the idea of virtual focal plane, you can ray trace any light rays. Okay? You see, the way we did before was we had an image, right? I mean, we had an object, right? So we say, okay, I'm going to draw two special light rays. One parallel to the optical axis, another passing through the optical center, right? But sometimes it might be necessary to know how to trace any light ray. Here's a light ray like this. It is not parallel to the optical axis. It doesn't go through the optical center. It doesn't go through the focal point either. It's just an arbitrary light ray. Okay. What are you going to do? Okay. What are you going to do? Well, let me tell you a little trick. It's called a focal plane. The idea is this. 1 over p plus 1 over q equals 1 over f. Okay. Imagine you have an object placed at distance p. Right? No matter how you draw light rays from that object, it's going to focus at a certain distance q behind the lens, right? Okay? Because when p is determined and f is determined, of course, q is also determined. Imagine if this is a light ray coming from a certain object. It's going to focus at the same distance behind the lens as any other light ray coming from the exact same object. Okay? So what I'm going to do is this. I am going to draw a light ray that is parallel to this so that I know how the other light ray behaves. This other light ray passes through the optical center. Now I know exactly how this light ray behaves. It's just going to go undeflected like this, right? Now, both of these light rays are parallel to each other. They are parallel to each other, which means if you imagine there's a point, there's a point on an object which emits both of these light rays. Since these light rays are parallel, that object must be what? Infinitely far away, right? Very, very distant. So p is what? Infinity. When p is infinity, what is q equal to? 1 over p plus 1 over q equals 1 over f. When p is infinity, q equals f. Which means, for both of these light rays, the image must be formed a distance f away behind the lens. Okay? For both of these, they should converge at the same point a distance f away. Now, here is a plane. Right? Here's a plane passing through the focal point, parallel to the lens. Okay, this is what called a focal plane. Okay, focal plane. Any point on the focal plane has exactly the same distance to the lens, and that distance is f. Okay, according to our lens equation, both of these beams should focus at the same distance away from the lens, and that distance should be f. That means this point, which is the distance f from the focal plane, should be the point where both of these light rays should come together. In other words, I can now figure out how this red ray is going to go. It's going to focus at the same point, like this. There we go. This is how you trace this arbitrary beam. Okay, so once again, what's the trick? The trick is to form a focal plane, which is a plane passing through the optical axis, passing through the focal point parallel to the lens itself. Any parallel beams, after going through the lens, must focus at the same exact location on the focal plane, a distance f away from the from the lens itself. Okay, this tells you how to trace this ray. After that, you just draw a focal plane and then draw another light ray passing through the optical center to find the point where they're supposed to converge, and then you connect these 2 points. There we go. That is the idea of the focal plane. So now you know how to trace an arbitrary light ray, okay? Not just special light rays. Another useful concept is the concept of virtual object. Now we know what a virtual image is, right? A virtual image. You extend the light rays backwards, they appear to be emerging from the same point. That's called a virtual image. Sometimes we have the idea of what's called a virtual object. Okay? Imagine you got a whole bunch of beams coming in. Now these beams would have converged here at a certain point, whatever that point is. But unfortunately, that doesn't happen because I put a lens in front of it. Okay? Or put a mirror, whatever I do, I put something in front of it. This instrument will alter these light rays so they will not converge at the same point anymore. Now my question is, what will the image formed by this lens? Okay, where is the image and what's the characteristics and so forth? Alright? Well, this calls for the idea of a virtual object. You know, a real object is supposed to be in front of the lens of the mirror, right? On this side, right? Light comes from there. And here, you extend these light rays back, you get something behind the lens or behind the mirror. No object is supposed to be there. Object is supposed to be here, the image is supposed to be there, okay? The object is on the wrong side, and then we say it's a virtual object. For a virtual object, what is the object distance equal to? Well, in this case, from here to there, and that distance should be a negative value, okay? Should be a negative value. So, don't worry about it. If you see a virtual object like this, just measure this distance, and if it's equal to 3 centimeters, you just say P equals negative 3 centimeters. That's all. Okay, now, as a special case, we have drawn the light rays in such a way that the extension of these light rays will focus at that point, and that point is a special point. It just happens to be the focal point of this lens. Okay, now that doesn't have to be the case, okay, but I'm using that case to illustrate how I'm going to get the get the image. Okay, so again, I can apply 1 over P plus 1 over Q equals 1 over F. I want to know, with the idea of a virtual object, do I get the right answer? Now, you know what's going to happen. Okay, in our case, the way I draw it, because I just put the focal point here, so the virtual object distance P just happens to be negative F. Okay, just happens to be that, because of the way I place the focal point. It's a special case. Now, we're going to find Q. Alright, we want to find Q. So 1 over Q equals 1 over F minus 1 over P. But P is negative F, so it's actually plus 1 over F. And that is F over 2 over F. That means Q equals what? F over 2. So it's supposed to be focused here, midway, right? Between the optical center and the focal point. Because Q is half of F. Now, is that right? Well, let's verify that with a ray diagram. You're supposed to get the same answer, right? How do I trace this light ray? Well, don't worry, I know how to do that. Didn't we just study the so-called focal plane? So here's what I'm going to do. I'm going to draw a focal plane right here. focal plane, right? And then what I'm going to do next, I'm going to draw a light ray that is parallel to this guy, but it passes through the optical center, like this. I'm going to draw this light ray. Now this light ray crosses the focal plane right here. That means that one must also cross the focal plane at the exact same point, right? So it's going to go across the focal plane at the same point. So let me now extend this. There it goes. Where does this light ray cross the optical axis? It crosses the optical axis here. Okay, you see this point is roughly midway between optical center and the focal point. This distance, of course, is Q. Alright, Q is about half of F. So you see, you get the same answer whether by drawing or by calculation. This is an example of the so-called virtual object. Okay, now I'm going to further apply the idea of a virtual object, and using that, we're going to study the so-called optical systems. In an optical system, I have more than one piece of instrument. I can have two mirrors, two lenses, or one lens of one mirror plus whatever it is, okay? Well, if I have a beam of light passing through all these gadgets, one after another, where would the final image be? That is my question. Okay, that is my question. Well, the idea is quite simple. You follow one simple idea. No matter how many pieces of instrument you have, you follow one idea. And that is, you're going to deal with the images one by one. Okay? Let's say I have one lens and a mirror. Encounter some lens first. Okay? What I'm going to do is I'm going to ignore the mirror. The mirror is behind the lens. I don't worry about it for now. Okay? I just worry about the lens. The object casts a beam of light passing through that lens without the mirror. Okay? Without the mirror, let me ask yourself, where is the image going to be? We call this image I1. I1 is the one formed by the first piece of instrument, which is the lens. Okay. Then the next thing what I'm going to do is I'm going to use I1, which is the image formed by the first object, by the first instrument, to use as the object for the second instrument, which in our case is the mirror. Okay. And that object will produce yet another image. Right? Will produce yet another image, which is the image formed by the mirror, and so on, and so forth. Suppose you get the third piece of instrument in line, then use the image formed by the second object, by the second instrument, to act as the object for the third instrument. Okay? So what's the general idea? You form the image by one instrument first, and use that image as the object for the next instrument in line, and so on and so forth. You always do that. Okay, that way no matter how many pieces you have, you can deal with them one by one. You can always get your final answer. And in doing so, we frequently have to encounter things like a virtual object, things like ray tracing or arbitrary light rays, that sort of thing. Okay, now we're going to look at a couple examples how this can be done.